Water is sometimes called the universal solvent. It's critical to the creation and evolution of life on our planet. With sufficient time, it can weather entire mountains away. In sufficient quantities, it can carry or release enough energy to alter weather patterns. In short, water matters, and so does its chemistry. In this lecture, we'll say goodbye to the metals and rocks of geochemistry and begin to consider the roles played by the greatest depository for water on our entire planet, its oceans, and we'll see how they behave at the molecular level. Water covers 75% of the Earth's surface. Most of us have heard this statement over and over, usually presented as a factoid in a grade school science course or a television science program. A beautiful photo of the Earth from space is often presented, sporting primarily a shiny blue ocean to validate the statement. But chemists know better. It isn't water that covers 75% of the Earth's surface. It's an aqueous solution. A molecular and ionic mixture based upon water, but containing immense quantities of many, many different dissolved solutes. Everything from salts to gold to carbon dioxide and molecular oxygen can be found dissolved in this 300 trillion gallon solution that we call the world's oceans, lakes, and rivers. Not only that, but each solute plays its own role in dictating how these bodies of water will behave. And that is something that we should all be concerned about because, after all, oceans do make up 75% of the surface of our planet. The chemistry that goes on within them can be used to create products like fuel, clean drinking water, and even more. So clearly, the chemistry of natural waters is worth a look. The ocean spans quite a significant volume of space. With a surface area of 129 million square miles, a maximum depth of about 6 miles, and somewhere around 200,000 miles of shoreline, the Earth's oceans are a vast and complex chemistry lab. By mass, our oceans are about 97% water. That sounds like a lot, and it is. But the remaining 3.5% or so is made up primarily of dissolved ions. Nearly all of the salt content of ocean water is comprised of just 6 ions. Chloride and sodium make up the lion's share of the dissolved ions, with some magnesium, sulfate, calcium, and potassium in there as well. The first chemist to analyze seawater was, by many rights, the first chemist of them all, Antoine Lavoisier. In his search for new elements, Lavoisier turned to the sea. He evaporated seawater and subjected the residual salts to successive extractions with differing alcohol-water mixtures to successively dissolve away each salt. Now, Lavoisier's samples came from the English Channel. And of course, a logical question would be, just how similar are those dissolved salts from water in the English Channel to waters from other locations? Is seawater seawater, or does it matter where it comes from? With such a vast area in contact with a huge number of varied shorelines, it stands to reason that differences might exist. In general, these proportions of ions in seawater are remarkably consistent. It was known as early as 1819 when Alexandre Marseille was able to experimentally confirm that ocean waters were remarkably consistent over a range of samples taken from the corners of the globe. But the real genesis of modern oceanic chemistry would have to wait for another 50 years. The story of oceanic chemistry and oceanography as a whole really begins in 1858 with, of all things, the construction of a British warship. The HMS Challenger, a Corvette-class warship with 18 guns, was powered by both sail and steam power. The Challenger served just as intended as a warship for 14 years. But then her purpose changed rather drastically. The credit for this goes to Charles Wyville Thomson at the University of Edinburgh. Thomson was able to convince the Royal Navy to allow a project in which the aging warship was retrofitted with dredging equipment and scientific instrumentation mounted where all but 2 of her original guns had been secured. Her goal would be to explore the biology and chemistry of the world's oceans as she sailed back and forth across the globe. The Challenger expedition sailed for 4 years, during which time the crew collected thousands of chemical and biological samples in a quest to better understand the natural system below the surface of the sea, including its chemistry. Challenger is probably best known for its stunningly productive haul of biological samples, discovering and collecting samples of over 4,000 previously unknown aquatic species. From the perspective of understanding the ocean's chemistry, Challenger was really just the very beginning. But the project piqued humanity's interest in the natural system of the world's oceans and the chemistry that they conceal beneath their surfaces. Natural gas is something that we usually associate with the subsurface of terrestrial locations. It's a product of petroleum distillation and is one of the cleanest burning hydrocarbon fuels available to us. But in the 1930s, as use and transportation of methane, the principal component of natural gas, increased, a problem was discovered. Pipeline workers began complaining of clogs forming in high-pressure gas lines in colder regions. It seems as though there was some moisture in the lines that was freezing, causing the clogs to form. Now, an investigation led scientists to the realization that the material clogging the line did in fact contain frozen water, but it was not your everyday ice. This ice had methane molecules trapped within a molecular cage of frozen water. The phenomenon of trapping single molecules inside crystals of ice had already been observed before. Michael Faraday had reported on this phenomenon happening with chlorine in water as early as 1823, more than a century earlier. Faraday had named the compounds clathrates, from the Latin term clathratus, meaning cage, inspired by the imprisoned molecules isolated within their jail of crystalline water molecules. This was a remarkably accurate description. So pipeline engineers went about trying to find a way to break up or prevent the formation of these newly discovered methane clathrates, considering them a nuisance and an obstacle to their mission of delivering their natural gas product. But that attitude changed in the 1960s, when methane clathrates were discovered naturally occurring in permafrost in Siberia. Several decades of prospecting led to the realization that methane hydrates are not just a pipeline nuisance or even a curiosity that forms in the most frigid parts of the world. They occur in many regions around the world, under the sea in the icy depths, first probed by the Challenger more than a century ago. What's important to understand here is that methane hydrates require a few things to form. Of course, the presence of methane and water are prerequisite. Since methane hydrates are solids, of course, we also expect to find them forming under conditions of high pressure and low temperature. And what better place to find cold, high-pressure conditions than the bottom of the ocean? Indeed, since the first discovery of the seafloor methane hydrates in the late 1980s, prospectors have found deposits on the shallow continental shelves of every continent. Oddly, they're not commonly found in the deep ocean where the pressure is greatest. So why is this? The reason goes back to the most basic criterion for the formation of methane hydrates. You have to have methane. And careful testing of methane from natural hydrates using sophisticated mass spectrometers has revealed that the methane contains a slim fraction more carbon-13 than one would expect based on this isotope's overall abundance in nature. Now, what this told scientists is that the methane was created biologically. Since carbon-13 is processed ever so slightly slower in biochemical reactions, it tends to accumulate in living things. And this signature pointed to bacteria producing the methane found in seafloor hydrates. Bacteria that live in the sediments on continental shelves consume organic matter as it falls to the seafloor. And these bacteria have a special metabolism that produces methane as a byproduct of their biochemistry. Dubbed methanogens, these bacteria are responsible for the methane-rich layers found in the rocks around them. The amount of methane trapped in hydrates is not well known, and it's still debated today just how much might be down there waiting to be released. Even conservative estimates, however, hint that there's more carbon mass locked in seafloor hydrates than there is contained in all the world's coal and petroleum reserves combined. Hydrates could change the world for better by offering a new source of energy to help power the world. But there may be a much darker side to these deposits as well. For starters, Methane hydrates tend to form on continental shelves, near areas where ships and planes most frequently travel. Some have theorized that sudden massive release of methane gas into the ocean by unstable clathrates might help to explain why some ships mysteriously sink in these regions. Imagine the ocean beneath a vessel suddenly filled with countless small bubbles of gas effervescing beneath that vessel. In theory, as the average density of the bubble-filled water beneath the ship drops, a ship could lose buoyancy and plunge beneath the surface before anyone knew what had happened. It's an intriguing theory, but one that has yet to be confirmed by direct observation. Now, perhaps more troubling than a theoretical culprit in the sinking of an individual ship, sudden methane release has the potential to have truly global effects, since methane is a greenhouse gas. Now, in our next lecture, we'll discuss exactly what that means, but for now it will suffice to say that adding large quantities of free methane gas to our atmosphere would be a very bad idea from a global warming perspective. Methane absorbs infrared radiation, and it acts like a blanket to our planet, increasing atmospheric temperatures when it accumulates. So releasing additional methane into the air can contribute significantly to increasing global temperature. Where things get really dicey is when we realize that methane hydrates aren't really all that stable, even where they formed underwater. Sometimes just a slight agitation by an earthquake or gentle heating by a warming ocean current can change conditions around hydrates and make them suddenly unstable. So even if you have your eye on that all-electric vehicle and think that natural gas might not be of any importance to you, it most certainly is important to all of us, not just because of the benefits it might offer when combusted as a fuel, but because of the environmental damage that it might do when released. Climatologists and geologists widely agree that spontaneous decomposition of hydrates might be a major contributor to global warming events. Picture this. Warming of the planet and its oceans triggers the release of large amounts of methane from hydrate deposits, which results in the buildup of methane in our atmosphere. This methane buildup promotes additional warming, which promotes additional hydrate decomposition, and a potentially devastating feedback loop can ensue. Such a loop might have already occurred once during the largest mass extinction our planet has ever encountered, the Permian extinction, some 252 million years ago, during which as many as 96% of all species on Earth were eradicated. So whether we use them for our own purposes, like a source of fuel, or simply try to understand their phase behavior to better protect ourselves from catastrophic environmental changes, methane hydrates are a material important for all of us to understand. Carbon dioxide is one of the most stable gases known. It forms quite easily during the combustion reactions that go on in our cars, during respiration that keeps us alive, and during the decay of most organic matter. It's an inescapable fact of living in an oxygen and carbon-rich environment like the one that we all enjoy every day. Oftentimes, we think of carbon dioxide in natural systems as a problem, in part because we humans create so much of it that we sometimes upset nature's chemical balance. Although it's quite true that CO2 that we generate can cause environmental problems, the presence of carbon dioxide in natural systems is also natural, and it turns out quite necessary. We'll visit carbon dioxide again in our atmospheric chemistry lecture, but for now I want to focus on its role in marine environments. We previously discussed how important carbon dioxide is to us as a buffer in our bloodstreams, and it turns out that the same type of chemistry is crucial to our oceans as well. Before the industrial era, the pH of the world's oceans was about 8.2. At this pH, the ocean is able to dissolve a great deal of carbon dioxide as carbonate ions. Many organisms rely on those carbonate ions as a material to create the essential corals and shells that they need to survive. Carbon dioxide gas in our atmosphere, of course, can dissolve into the ocean, and we know that Henry's law predicts that as the partial pressure of carbon dioxide in the atmosphere increases, its solubility in the oceans should increase proportionally. So, what's the problem here? How does increasing the amount of dissolved carbon dioxide in the oceans actually reduce the availability of essential carbonate ions that so many marine creatures depend upon? So let's say you are one of these small marine organisms that relies on carbonate to make your shells, for example. Well, the reaction that you're most concerned with is actually one that doesn't have anything to do directly with carbon dioxide. It's right here. It's the equilibrium between bicarbonate ion and carbonate ions. Now, most marine animals have to sequester their carbon as carbonate ions. This is how their chemistry works. So it's the concentration of these carbonate ions that's going to have the most profound effect on their ability to thrive in their environment. So to understand how the presence of CO2 affects this equilibrium, we have to turn to the Henderson-Hasselbalch equation and realize that when you hydrate carbon dioxide, you make carbonic acid, and you add protons to the environment. In other words, you continually acidify the ocean as you continue to generate these nonmetal oxides through the burning of fossil fuels. So let's see what happens as we change the pH of the environment in which this equilibrium is that one that's critical to us. Well, the pKa of hydrogen carbonate is about 10.3. And the Henderson-Hasselbalch equation gives us a way to relate the pH of the environment that we're dealing with to the ratio of dissolved carbonate to bicarbonate ions. Now, the original pH of the oceans before the Industrial Revolution, at least, was about 8.2. And if we put those numbers into our equation, we find that about 0.8% of the dissolved bicarbonate in the ocean is actually present as carbonate ions. Now, that's a relatively small percentage, but that's a lot of material when you consider just how much of this is dissolved in the world's oceans and how large they are. But over time, as we continue to burn fossil fuels and introduce these nonmetal oxides into the environment, we introduce more and more acid. And as that acid begins to change the pH of the oceans, bringing it down, we anticipate that this equilibrium will shift in accordance with the Henderson-Hasselbalch equation. Specifically, if we take a look at the pH that we're down to now, about 8.1, you'll notice that we're down to about 0.63%. So that means that we've already lost almost a quarter of the carbonate that was previously dissolved in the oceans simply because of the pH affecting this equilibrium. But it gets worse than that. If you believe the experts, in the next century, we can anticipate that the pH of the world's oceans will drop by almost another half of a pH unit. So let's put those numbers into our Henderson-Hasselbalch equation and see where that gets us as far as the amount of dissolved carbonate as acid builds up. Well, at pH 8.0, we're down to about 0.5% carbonate. As we continue, pH 7.9, another tenth of a point on the pH scale, loses us another tenth of a percent of carbonate. And when we reach the projected pH levels for the ocean in 100 years, if all things stay the same, we find that we've got 0.2% of the dissolved carbon in the oceans present as carbonate ions. That's a four-fold decrease from the original pre-industrial revolution values. And dropping the carbonate ion concentration that much is potentially dangerous. Essentially, what's going on here is Le Chatelier's principle is driving the chemistry of our oceans. As the proton ion concentration increases as a result of human activity, the equilibrium shifts in a way that relieves that stress, consuming carbonate ion and forming more bicarbonate ion, which can't be used in the same chemical processes that carbonate ions are. Once this concentration reaches a critical level that, frankly, we don't know what it is, we can't predict it. But once that level is reached and the biosphere becomes a little bit more chaotic, we really don't know what's going to happen. All we do know is that a number of marine organisms won't be able to survive if we continue driving down ocean pHs the way that we have in the last century. This is a potentially serious problem, as human activity pushes atmospheric carbon dioxide levels higher than normal. The ocean itself dissolves a sizable fraction of that CO2 in accordance with Henry's law. Now, this potentially creates an environmental change so drastic that coral reefs and shellfish simply can't adapt. There is no simple solution to this problem except for changing our habits as a species and the amount of carbon dioxide that we pump into our atmosphere. So, the data collected by the scientists on the Challenger expedition supported Marseille's principle that ocean composition is essentially uniform, although its salinity can vary. Now, even as sampling and testing methods became more and more sensitive, it seemed that the world's oceans were basically one giant solution with a fairly uniform and predictable chemistry. This may sound a bit unintriguing at first. It seems that, for the most part, the ocean can be studied from anywhere by anyone at any time, with very similar findings. Not the most exciting of subjects. But the fact did excite one very notable chemist with one very grandiose agenda. Again, we find ourselves discussing Fritz Haber, the eccentric and infamous German chemist. By now we know that Haber was inexplicably loyal to the German government that had shunned him, while simultaneously exploiting his genius for his entire career, and indeed his entire life. After World War I was over, Haber, like many Germans at that time, felt that the reparations debt forced upon Germany by the war's victors was burdensome and unfair. Rather than complain, Haber decided to do something about it. And what he decided to do was a blend of megalomaniacism, entrepreneurship, and a touch of good old-fashioned insanity. You see, it had been known for some time that samples of seawater contained much more than just the 6 principal salts that we looked at earlier. That small remaining percentage of dissolved material is comprised of many other ions and elements, and among them is gold. The amount of gold in seawater is vanishingly small, about 10 milligrams of gold per ton of seawater. Now, Haber figured that he needed about 50 tons of gold to bail out his beloved nation. That may sound like an insurmountable amount of debt, but consider that the 300 trillion gallons of seawater currently filling the Earth's oceans weigh just over 3 trillion tons. That estimate would put over 30,000 tons of gold dissolved in the oceans of the Earth. If Haber was right, he only needed a fraction of that to reach his goal. Haber no doubt envisioned massive seaside plants, processing tons and tons of seawater daily, or possibly ships at sea, sailing across and through the most gold-rich area that could be found, processing the seawater to extract the gold. In the years following World War I, Haber secretly obtained funding and an opportunity to ride aboard the Hamburg-American ocean liner, the Hansa, in 1923. This was so that he could discreetly survey the Atlantic Ocean for gold. Much to his dismay, he did not find the quantities of gold that he was hoping for. Haber would make no fewer than 3 additional attempts to find a region of the sea that was rich enough in gold to make his methodology a cost-effective way to collect it. But he was at the mercy of Marseille's principle. Everywhere he looked, he found the same disappointing result. His estimates of how much gold were in the seawater were just too high. Since then, the extremely low concentrations of gold in seawater have kept Haber and many others from staking their claim to a massive fortune dispersed throughout the deep. But all those failures still haven't dissuaded others from trying their hand. And maybe one day we'll find out that they weren't wasting their time, but we'll have to wait a while. So let's review this lecture. We started by thinking about the role of water in natural systems on Earth. We reminded ourselves that pure water is a very rare thing, and that the oceans, lakes, and streams covering the globe are actually complex solutions. The dissolved solutes in the ocean can have a profound influence on everything from environmental effects to commercial applications. And we discussed the rather remarkable fact that the ocean, vast though it is, seems to be fairly well mixed, having a uniform ratio of dissolved solutes practically anywhere you look. We thought a bit about how pressures and temperatures at the bottom of the ocean are quite different than what we experience on the surface, and that this unique environment can lead to the formation of some very unusual materials. Materials like methane hydrates, which might someday serve as a major fuel source or a driver of rapid climate change. We also considered the role of dissolved carbon dioxide in the oceans. Particularly, we thought about how the sequestration of atmospheric carbon dioxide into the oceans can throw off pH conditions, and those pH conditions are necessary for a variety of creatures to manage their carbonate uptake. And finally, we crossed paths yet again with Fritz Haber, And we saw how even Haber's remarkable genius and unfathomable motivation to aid his country were not enough to make his dream of harvesting gold from seawater a reality. So we've concluded our discussion on the chemistry of the oceans, and it's time to continue onward, moving into the chemistry going on all around us and above us in that thin layer of gas bound to our planet. Atmospheric chemistry is our next topic. For many decades, most chemists thought about Haber's quest for gold from seawater as a pipe dream, something that could never really be accomplished. But in recent years, certain attitudes about that have started to change. And that's because in 2013, a research group reported on a molecule used by gold-resistant bacteria to complex or chemically interact with gold ions in solution and cause them to form solid gold nanoparticles, very, very tiny pieces of gold. Now, the material that they use is called delphtibactin. And again, it complexes one gold atom and turns it from an ion into a neutral gold atom, which then forms these particles, these aggregates, as they come out of solution. And of course, that's exactly what Haber had tried to do a century ago. Now, this molecule, delphtibactin, has a molecular mass of about 1,033 grams per mole, and best estimates at the cost for producing it place its cost at about 25 cents per gram. And of course, gold itself has a price that fluctuates, but is about $40 US per gram. So we want to do a quick cost analysis here. Now, naturally, there are a lot of other costs associated with a project designed to get gold from seawater, but let's ask a simple question here. Is it worth it? Is it going to cost so much money to just get the delphtibactin that we need that this project is hopeless, or is there really a chance this could work? So again, we want to use this delphtibactin to complex a gold ion and take it out of solution and create a complex which eventually leads to the production of little tiny microscopic gold nuggets that we can collect. So the question really comes down to this. If a gram of gold costs $40 and a gram of delphtibactin costs about 25 cents, then let's ask ourselves if it's worth trying. Now, to do this, we'll need to keep all of our information in order here. And remember our reaction here. We're assuming that it takes one molecule of delphtibactin to get one ion of gold to precipitate into these particles. So using these very, very simple assumptions, let's do the math and see if it's worth pursuing. A gram of gold is going to cost us how much to get, assuming that all of these assumptions about our delphtibactin are true? Well, gold is 197 grams per mole. And delphtibactin reacts in a 1-to-1 ratio with the gold, at least that's what we're going to assume. And of course, we know that these delphtibactin molecules weigh 1,033 grams per mole and cost about $0.25 US per gram. Now, my calculation gives me, when the unit analysis is done, grams of gold canceling, moles of gold canceling, moles of delphtibactin canceling, and grams of delphtibactin canceling, telling me how much I have to spend on that material if I'm going to attempt to collect gold and make some money here. And it turns out that to get that amount that we would need, again, assuming that all of our other assumptions were true, right, is actually about $1.31. So now you can begin to see why people get so excited about this concept. Current efforts to use this as a means of getting gold from seawater, unfortunately, aren't that much better than standard chemical extraction techniques. But the fact that it was discovered so very recently and hasn't been fully studied and characterized leads many to believe that maybe one day delphtibactin will be the key to solving that riddle that Haber had tried a century ago. Someday, we may actually be able to extract gold from seawater using a molecule created by a bacteria.